This is a video for AQA Further Pure, second order differential equations 2, non-homogeneous equations, 2.2, using a trial function to find a particular integral. We've seen this differential equation in a previous video, and we've actually worked out its complementary function by looking at the homogeneous version of this when that is equal to naught. And that complementary function turns out to be y is equal to ae to the 2x plus be to the minus x. We need to think about the particular integral for the right hand side, and again, if you've looked at the previous video, you'll know what the answer for this is because we quoted it in the last video. However, let's have a look at how we could try something out with that. We're going to try using something that is of the same form as the right hand side. So we're going to try y is equal to ax plus b, and I'm using little a and b here to distinguish between the arbitrary constants I've got in the complementary function. Well, if that's the case, then differentiating, I'm going to get that dy by dx is equal to a, and I'm going to get the second derivative, d2y by dx squared, is equal to 0. So if I substitute this into the original equation, I'm going to get 0 minus a minus 2 lots of ax plus b is equal to 3x plus 4. Now if we just expand that a little bit, we're going to get minus 2ax minus a minus 2b is equal to 3x plus 4. So if I compare coefficients, well, if I look at coefficients of x, I'm going to get minus 2a is equal to 3, and so that tells me that a is equal to minus 3 over 2. And if I look at the constants, then I'm going to get minus a minus 2b is equal to 4. But I know a is minus 3 over 2, and therefore I end up with b is equal to minus 5 over 4. And so my particular integral is y is equal to minus 1.5x minus 1.25. There's that working written up so you can follow it a bit more easily. There's our complementary function that we saw in the previous video. Here's the trial function, and we're using the same shape. This is 3x plus 4, so we're using the same shape, ax plus b for y. Differentiate a couple of times, plug everything into the original equation, and compare the coefficients. And if I do that, I end up with that for my particular integral. So now looking at this whole differential equation, the complementary function is this, the particular integral is this, and so the general solution is the sum of the two. So this bit here is the complementary function, and this bit here is the particular integral. Now I know that if I substitute this back into the original equation, then all of the bits for the complementary function, when I sub them back into here, are going to give me 0, and all of the bits for the particular integral, when I sub them back into here, are going to give me 3x plus 4. So it really should work out. So in summary then, here's my non-homogeneous differential equation. First solve the homogeneous version to get the complementary function. Look at the particular integral as being the same shape as the fx, the right hand side function, and substitute that back into the equation to sort out the parameters for that, and then the general solution is the sum of the complementary function and the particular integral. The next video in this sequence is 2.3, particular integrals, polynomials.